So, title of the talk is C++20 in breadth. And I don't know if you've seen any of my in-breadth talks before, but the principle is I'm going to cover everything that's changed in the C++ core side of the language, less the library this time because time constraints. And also, we had a really good talk on that yesterday anyway. But there'll be very little detail. This is a sampling of everything, and to my best of my knowledge, everything that is changing in the new version of the language. So you will have the menu of, oh, that's interesting, I now know what I need to go and do more research into. Because a lot of these features, when we've got all the big, highfalutin features, a lot of the smaller features get left by the wayside. And yes, we do spend a fair bit of time on the big boilerplate features. These are what people want to hear about, but I'm trying to make sure I have time to cover everything in breadth. In particular, I'm not sure if I've succeeded. I've tried to actually get the talk drilled down to about 60 minutes, so there's plenty of time for interaction as you figure out which details you actually want me to talk more about. But it means I'll be talking to bullet points rather than having prepared material because I don't know which points you're going to want to jump in on. So with that, we'll get going. Takeaway point is C++20 is big. Really big. Inevitable Douglas Adams quote. If you don't know where this quote is from, there's a real treat ahead of you. So, how do we get to C++20? Just a little quick bit of background. The committee puffing their chest and saying this is what we've done. Back at the end of, in early 2017, we finally published C++17, and that's when we had the chance to finally start work on C++20. As you can see, we've had roughly 6 or 7 meetings over the space of 2 years to try to move the language forward. How much can we do in the space of 2 years? Well, actually slightly less than 2 years because we had a cutoff date of November last year for any core language feature that was likely to have an impact on the library. We don't want to end up at our final meeting in Cologne in July finding that the core language has changed in some way that massively impacts the library specification. We're spending all our time fixing that up rather than doing the new library work. Likewise, there was a final deadline for anything that is new coming into C++20. Had to be at least approved through the evolution groups of both library and core as of the last meeting. So we do know what a feature-complete C++20 should look like. The trouble is, with this fancy screen,
I know it's not a button though because there's such a thing. This is probably good.
That will do, okay. That's better. We've got one more meeting to come to finally land all the work we've approved. And we hope we can complete that work in there. So I might be describing a few things that don't actually make it into C++20, but I believe we've got a really strong shot at everything I'm talking about. And the reason C++20 is so big is it's more than 2 years' work. The 6 different TSs here that we've been working off on and off over the last decade. And large parts of the work in these 6 TSs is finally shipping as part of the main language standard now. With a quick page count just to see how much things are changing if I'm saying it's so big. Well, it turns out that the core language is actually 28 pages shorter, which fooled me, and then I realized, well, we've changed the paper size that we're printing the standard on, and that seems to be the biggest impact, although core have done a very good job of distilling and pulling out words they don't need as they're adding new ones in. So they've done a fairly good job. Library, we just keep adding stuff. So we've got 130 pages added to the library so far, most of which seems to be related to date, time, and chrono, and ranges. As I'm not going to talk too much about library, we'll get there shortly. Other things we've been doing that will make the standard itself much easier to work with has been editorial reorganization. So if you're familiar with the standard as it is today and which clauses you go to find certain pieces of information, you'll be aware that some things are very unrelated and scattered around the standard. So those, especially in the core language where the rules for temporary objects were buried in the rules for constructors, which is a very strange place to find them. So we managed to reorganize that so everything's a bit more coherent and consistent. But it also means if you're familiar with clause numbers of where to find things, everything's jumbled up and moved around a bit. So if you're ever trying to quote somebody for a reference in the standard, things have named stable tags, and as the numbers get re-indexed, those always stay the same. And that's how we actually get to continue working on this as the committee and still know we're talking about the same piece of text. Another large thing that's taking a lot of library time is we're actually redrafting a lot of the ways we describe requirements on functions and classes in terms of preconditions, postconditions, compile time constraints, what's supposed to be an error, what is supposed to be a spinable condition. We've got much clearer language to describe that now, but that does mean an awful lot of time is spent just redrafting to make the existing specification cleaner and clearer, in addition to adding all the stuff we'll be talking about. So, as we've got one meeting to go, how much do we still have to land? At last count, I saw there were 18 core proposals in flight with full wording, and maybe a couple more that are supposed to be landing and haven't been shipped with the wording yet. So that's a lot, but about the scale of what we've done in a typical meeting. There's 60 library proposals as far as I could tell from our work queue. The work queue is even larger because we've got lots of TS work, but that's ambitious. So if I was spending much time talking about library features here, I'd be a lot less confident in how many of them are going to ship. But there are still significant library enhancements that will be coming in the next 3-4 months. And to put those numbers in perspective, of the previous 6 meetings, so we've managed to find about 65 core papers, so that's about on a par, and 80 library papers, with 60 to do in the one next meeting. So, but they have already, many of them have already been partially reviewed, so they're making progress, but there's still a lot of work to come. And some very busy people for the next 3 months. So we go back to C++20. There's this pleasant little coincidence that it seems many of the big features, the headline features people want to talk about, seem to have a C0 in them. Unfortunately, the most popular feature at the bottom is modules, and it breaks my rule. Wanted to call it components, but I don't think anyone would ever let me get away with it, apart from maybe John. So these are in my mind, the 7 pillars of C++20. Concepts has been coming for a long time. Contracts is something we've had several attempts, and we've finally got a version that's going to ship. Compile-time programming, whether we love it or loathe it, it's been an establishment of C++ for a long time now. So just getting better ways to do that. The new comparison operators coming in, maybe not quite as big a pillar as the rest, but it will be one of the very observable features coming away from the language as people start getting more familiar with it. There's always work on concurrency. We have a working group just working on concurrency. So there'll always be a pillar every new standard comes out as far as I'm concerned. Coroutines has finally landed, and as I say, modules is a popular feature. But I always like to start these things with, let's make C++20 smaller. Which things are we actively retiring from the language now? So if you're worried about compatibility, if you're using any of these things, these are being removed from C++20. First of all, we have the empty throw specification, because you simply replace it with no except. It's been deprecated for a while. Pretty much all of these have been deprecated for a while. Sorry, I'm having trouble with my teeth here. And along with that, we remove the uncaught exception that went along with the whole exception specification feature that got removed a while back. In the standard library, we have the adaptable function API. Bind first, bind second, was removed in C++17. But we still kept the type defs around that supported that protocol because we had the negators, not 1, not 2, that hadn't been deprecated earlier. So they stuck around for an extra release. So those negators, not 1, not 2, have been replaced by not fun, finally go away. And when they go away, we can finally remove the requirement that all those type defs are there. But note that every time something leaves the library, it becomes what we call a zombie. The word remains reserved for the library for previous standardization, which means the library vendors can continue shipping and supporting those old APIs for as long as they like. It's up to the library vendor, though, to choose when they discontinue support. The standard itself is no longer actively tracking these things as the language evolves. Same way, these features were all deprecated in 17. The temporary buffer API, get temporary buffer, return temporary buffer, raw storage iterator, the ceased headers that were there for C compatibility but did nothing like ceased bool, they go away. Shared putty unique. Who thinks shared putty unique is a safe function to use? Ah, good, the message got out and nothing more to say there. Is literal and is pod are two type traits that have gone away. And the definition of pod in the core language has gone away. Is pod should not be on that list of things that have gone away. Is pod has been deprecated, not removed. I think it's, There were two type traits removed. I've got the wrong one listed there. I think it was result type was the other one, because that's replaced by invoke result. Yeah, that's why it's got a slight error on it, sorry. But lots of slides, bit of a rush. In terms of compatibility with existing code, we're reserving 8 new keywords. And some of these follow our standard now uglification practices. So we've got char8_t. We've got some co_ keywords that are used by the code routines feature. Concept and requires, on the other hand. There's a real chance that popular English words like that might end up clashing with some of your code in some way. We had no real alternative there other than getting really awkward keywords, and you didn't want that for expressing such a fundamental part of the language. So in that case, we bought the nice word. And we've got a couple more things related to some of the compile time programming. We have 2 new contextual keywords, which means in some cases where you're using import or module as an identifier, you might find it's actually got a different meaning in that context now, and you can no longer use that name in just that particular way. Often there's a way to disambiguate. An example here. Import int error. Okay, it's a variable named error of type import with template parameterized on int. Perfectly good code in C++ 17 will give you an error in C++ 20, because that looks like you're trying to import the header angle bracket int. And instead, if you disambiguate by just using the fully qualified name, corresponding to the global scope double colon, that makes it clear that this is not trying to use the contextual keyword to do an import, whatever that means. Other compatibility gotchas, as you're making the transition up. U8 characters and string littles are now a different type. We've got char8t you saw on the previous slide. So any code that maybe does an auto deduction of those, passes them through what's it called, a type deduction in function templates, that will be fine, but it'll be a different API you're getting because they're deducing different types. On the other hand, if you're trying to assign these literally to a char star or a const char star, that code will no longer compile and will need to be addressed. Integral types are now going to be mandated as two's complement. I'm not sure that's going to be a real problem for anyone, apart from maybe some vendors who have really old platforms who might still be trying to support them. But that one I think is just good forward progress. It seems there was a little hole in the core wording for everywhere that a incomplete type wouldn't be allowed. So if you've got arrays of incomplete type, you weren't allowed to have arrays of abstract types. But where you try to use them by value, for example, you might be able to parse the code with an incomplete type and say, yeah, as long as I don't call it, we're fine. Call it, I'll have that error. We've consistently married up things like return values can't be the way we specify. You can't have abstract types as return values from functions. This is something you can't have, I'm gibbering here because I'm trying to get through things fast without trying to duck into detail. That's the nature of the talk. But yeah, we married up when something can't support an incomplete type, it shouldn't also support an abstract type. So that was a little clean up in the language. Whether that's going to find any errors in your code, I don't know. If your code fails to compile, it was probably an error, but we probably weren't telling you before. And one of the interesting corner cases, types with deleted constructors. If that was our only constructor, it would be an aggregate. So I could delete the default constructor, but I could still to value initialize that thing because it doesn't use the default constructor to initialize it. It actually uses the aggregate initialization rules. I think it was the same for the copy constructor. I could delete the copy constructor and I could still make copies because I would aggregate initialize with list initialization. And yes, I still get an aggregate. So the new rules for defining what makes an aggregate is if it's got a deleted copy constructor or any other constructor, it's no longer an aggregate. And again, whether that's going to flush out issues in existing code, I don't know. If it does flush out issues, it's probably because someone's trying to be too clever rather than necessarily doing something unintentional. But having a simpler, more coherent, teachable language, that seems to be the right direction. On the library side, in terms of, again, backwards compatibility, because you're looking to move forward into the brave new world we're about to talk about. Almost there. The order and number of template parameters on the function templates for a lot of the library algorithms and so forth, where the intent is to deduce the type at the function call, those are now unspecified, the ordering and the number. So you're not technically allowed to do an explicit instantiation with the template parameters when trying to use a deducible parameter in the standard library. Now, how much we're going to take advantage of that in early implementations, I don't know. More likely to be an issue of the new features as we add, because library vendors are notoriously unhappy if they have to go back and break ABI compatibility with existing code. So we're unlikely to break existing code doing this. But we're putting down the rules and saying, that's now within our freedom to change, and you really don't want to do that with any of the new features we're adding. A more controversial one is you can no longer take the address of any standard library function or static member function of a class template or a class unless it's what we've explicitly marked to be an addressable function, where you really do expect to take the address or take a reference, which means when you want to pass these things as function pointers into algorithms, no longer allowed. Whether you get an error at the point of use, or simply say, well, okay, if you have an overload there in the future, that will become ambiguous and you're out of luck. We're not guaranteeing we'll detect all those errors early for you, but when they do turn up later as the library evolves, we've put you on notice now that you shouldn't be doing that. As far as I can tell, the main set of addressable functions in the standard library are all the I/O manipulators, because we rely on taking their address when we're doing I/O streams. So their whole purpose is to have their address taken. As far as I can tell, we've not put that mandate in for anything else yet.
What's the workaround for that? Lambdas?
Yes, what's the workaround for that was the question. And the simple suggestion provided at the same time is, should we use a lambda? And yes, a simple lambda that directly forwards the arguments through will solve the problem.
What does it mean by unless it's explicitly permitted? Is there a keyword for?
It's not a keyword. It's in the library specification itself. We have new words of power. Please repeat the question. Now, if I ever deviate and go back looking over here, in case someone remind me saying, folks, on the camera, can't hear when I get a question from the audience. Can you repeat the question for me again? Because I've lost my mind.
No.
Yeah.
How do you explicitly
Yes.
permit something?
The question is, how does the library explicitly permit your ability to take the address of a function? And no, there's no new syntax in the language. We're not adding new attributes. It's what we call words of power in the standard to say, if the standard specification says this is an addressable function, or these functions are addressable functions, it means they're in the set of things that you can take the address of. And finally, the ADL customization points that we define. So swap, begin, end as free functions, empty, data, a few of these others. We expect users to respect those properly if they define them as free functions discoverable by the ADL in their own namespace. So that's a set of library compatibility changes. Most of these, they're not obvious, they're a bit subtle, but they do unlock our ability to develop libraries more maintainably easily in the future as we're that don't collapse under the weight of everything we're building. And last thing, I love to clean up the standards, so I always lead with this material. Things that we're deprecating that are currently and will continue to be well defined, but you might start getting warnings from your compiler when you start doing some of these things. So arithmetic conversions on two different enums. So I've got enum E1, enum E2, and they add E1 plus E2. That's now deprecated, the promotion to integer to do the integer arithmetic. Or adding a float value there. So we're not stopping that today, but you might start getting deprecation warnings. Comparing to arrays. It doesn't mean anything, it's not very useful. What you're actually doing is the array decays to the array pointer and says, are these two the same array? Literally, do they have the same address? It just fell out of the grammar, it wasn't necessarily what people wanted. And as we've worked on new features to deal with comparisons, as I alluded earlier, we're disallowing that for the new feature coming in, and we're deprecating that, so you'll start getting warnings that, are you really sure this is what you wanted to do from your compiler, hopefully, on these things? With lambdas, the implicit capture of the this pointer was kind of subtle and confusing, and when you use this in your lambda, does it mean this on the lambda or this on the captured thing? So the implicit capture of this is now deprecated with a view to removing it in the future. And the intent is we've got a new feature, you explicitly add this to your capture list, and that captures the this pointer from the context where you're using a lambda. Anything you see in this wonderful violet color is things that we are hoping to land in column. They've not landed yet, but we have good confidence they're going to land. In this feature, we're going to deprecate the use of commas or comma expressions in square bracket subscript operations. So that opens up in the future. We might therefore be able to actually have multi-index array parameters. We're not going there yet. But I'm saying this is confusing because people often misread these things happening. They don't realize that's a comma expression when they see that. And so we're going to deprecate that in the hopes that we can move forward in the future. And volatile. Who wants to get rid of volatile? No. Again, this paper is due to land at the next meeting. It's an interesting paper that slices and dices through why volatile exists and how just making it a regular CV qualifier caused more problems than we intended in C++. So it's dialing back to say, well, there's still reason for volatile. It exists for dealing with regular systems in certain parts of your memory that might change under the covers without you knowing about it. But it's largely down at the C compatibility level. The way it's invaded the type system and infiltrated the whole language is probably not something we actually want to maintain going forward. So, there are a series of things we looked at deprecating. So compound operators like plus plus, minus minus, plus equals. On volatile scalar types, so integers, floats, pointers, deprecated. Assignment chaining, so A equals B equals C equals D. On volatile scalar types again, deprecated. Volatile qualified member functions was too controversial, so we're still stuck with those. But we did look into it. Volatile qualified function parameters. So I'm writing my function, I take my arguments, and I put a CV qualifier on my pass-by value arguments, which has always been a bit of an odd practice to begin with because they're all the same overload. It's a restriction on the implementation, not the caller. But using volatile in that context now, deprecated. Similarly, volatile on return values, deprecated. And finally, the notion that the standard library is going to make allowances for volatile is going to be restricted just to the type trace library, because this is an introspection reflection type library. You really do, this is the one place you do need to get hold of that. The atomics library, which was built around volatile by its nature, and numeric limits, because numeric limits is against introspection type API. It's effectively a very early type trait. Any place else in the library that makes accommodation for volatile, going to be deprecated. Other things getting deprecated in the standard library. Relops, move iterator, dereference through the arrow operator. The ispod trait that I mistakenly said was being removed, it's just being deprecated. The free function atomic API to access shared pointer is being deprecated because we're trying to provide something better this time around. Basic string reserve with no arguments, which is basically interpreted to be an intent to be shrink to fit. But it was never clear anybody actually did that, or that's been deprecated and hopefully can go away sometime in the future. And finally, there's some free functions in the file system namespace, U8 path. This are again being deprecated because we're reviewing our whole approach to Unicode and UTF-8 in particular. So, talking about some of the new stuff, that this is why you all came here, I'm sure. And probably the number one feature I hear people requesting for C++ is modules. So, what is the notion of modules that we're going to be landing in C++ 20? The essential model is it's a way to build our software without relying on hash include, recursively copy-pasting millions of lines of source into every translation unit. What it is not, that people kind of expect from other languages, is a binary distribution format. You do not compile your module and keep it as an opaque thing to say to someone, just import my module now and here's everything I will ever need, I can compile and link against it. Not the problem we're trying to solve. Purely a better solution to hash include. In particular, we will often require the full source to that module, including not just the header equivalent, but what would have been in the CPP as well. We will require the full source. So the compiler can see that source, parse and translate the interface for that module, and then it knows what you've imported and what's available. Of course, the intent is that implementation will do something smarter than recompile the whole module every time you want to import it. They're going to do some smart caching thing, which hopefully will then give us better build times, which is one of the main objectives people have been trying to achieve by getting rid of all that. Go back to the file system, copy paste all these files and build. There's been lots of optimizations around that already, particularly things like precompiled headers and the include guard optimization so that the compiler knows not to go back to the same source all the time. And as I say, with the idea of caching precompiled import files for your modules, be kind of similar to the include guard optimization. We've done it once, we know where it is, we can keep mapping it off disk, and hopefully nothing else changes. And while we don't have binary distributability of these modules, the same compiler of the same vintage will know how to read its own files. It is noted that even different builds of the current GCC compiler in their experimental modules feature cannot read each other's precompiled interface files because they're encoding that build information into the file format just to make sure they don't accidentally try and read something that's doing something slightly different. So it really does mean compiling locally, I'm fine, everything's going through the same compiler, but I should not expect to distribute the output of compiling and building a module. Another big benefit we get, and I'll go into this example I have following, is macro isolation. So when you token paste by hash include, you just copy paste all that source to make one huge million line file. Macros run rampant over everything and you can't control them. Hopefully with modules we can do a little bit more about that. We have to be a bit more careful about how we're exposing and exporting macros. We don't want to shut down the preprocessor because we still want to interoperate with the old world. Things like standard platform OS headers will be defining things in terms of macros. We need to use them. But we can hopefully contain all of the problems that come from macros in this new model. We have module level linkage, which means I can have some entities now that live within the module and don't leak out of it, which again just gives an extra level of hygiene as you're trying to build larger and larger systems. And a clear feature we've been That's what we're trying to make sure works, is that there will be a simple migration path. It all interoperates with the existing code with hash include today. Because we don't have the entire world migrating to C++20 at once. And in most organizations, it'll be experimental as different parts get to migrate at different times. It's important that the model we have for building source is backwards compatible. So, quick example I'm going to talk about, macro isolation, a few of the ideas that come out of modules. You're finding a module. First of all, we have the module keyword that says, this translation unit, it's a module. And I'm part of module demo. Module demo might be made in many files. I am one of those files that goes into building module demo. Then we get a preamble where we can import include and say, I'm depending on these other things. Didn't put an example, but you can also import a header as opposed to hash include a header. But when you include these headers, they're treated as if you were importing that header. Which means while I'm in the module preamble, any macros defined while I pass stdlib.h are not active when I pass the subsequent mycode.h. And this is where we get the macro isolation. The macros from the things I explicitly include will definitely come into my code. That's by intent, but they will not interfere with each other. And if I was relying on a transitive property that this macro is defined in this header before me, that I haven't explicitly included in my header because I just assumed it would always be there, my code might start failing to build this way. So the idea is, as you migrate towards C++20, you want to at least make sure all your headers are idempotent, that they don't have accidental dependencies on things they happen to build because the world around them already included everything they needed down the build paths you happen to use. And that's something that's worth trying to catch in your code today. Now you'll have an easier transition forward, and your code will be clearer for it anyway. The preamble ends when we get to the line that says export module demo. Now this does two things. It says I've got to the end of the preamble. It also says I am the interface module for this, interface unit for this module. I now get to define the whole interface that this module exports. And that's about as far as I really want to go down this line. There's going to be much more important and useful talks about modules elsewhere. All of my 7 pillars, each of those is easily several 90-minute talks, and I've got to somehow keep this turf and keep moving. But I do have one other interesting corner to talk about in modules that is going to take a little bit of wrapping our heads around. This is something that isn't a problem today and becomes an interesting concern as we get to modules. And I believe this will still be how things work at the end of Cologne. But people are still playing around with different points in the design space here just to see if there's things that can be cleaned up. But if we look here, I've got my export module foo. I have a class internal that I am not exporting. Internal just has a function call operator. And I export a function in namespace demo of module foo called test that returns an internal by value. And I go into my main program. Main, I import foo. I say, oh, also x equals, I will call demo.test, demo.test. Yay, I got something. I'll try and name it. I know that it's called internal. If I name it, it doesn't work. I do not have access to the name internal. But structurally, I have access to everything that internal can do. So I can make a copy of it, as long as I don't try and name it. I can make an alias type to that name if I want to use that name. And I can indeed invoke the function call and return that from my main. So in this sense, internal is reachable, but you cannot name it. It's not accessible. Accessible is the wrong term because that goes back to public, private, and classes and so forth. But it's reachable but not visible. And this will be an interesting thing that we're going to gain experience with as time goes by. Moving on to the concurrency features. This is not my domain of expertise, but I do spend far too much of my time in library committee time wordsmithing the work that comes out of SG1 to try to make sure that we've got robust contracts the way that a library would like to say them. So I know too much about this while I know nothing about this. It's a horrible balance. In particular, the big thing coming in, of course, we're going to revise the memory model again. as we get to nail down with a bit more precision and specification some of the natures of how you can have happens before with your atomic operations on some of the weaker architectures like Power and ARM. They really do need subtle ways to say how strongly something happens before another thing. Or maybe it could simply happen before, there's coherence happens before something. There's a variety of terms in here that I am not the right person to talk about. And if you do not get down at the level of atomic operations when you're writing your C++ code, probably not something you need to talk too much about either. But for those people who really do get down to the metal, and where performance really matters, and the different performance characteristics of the weaker memory models on these modern architectures really matter, we're getting down to the fine details and making our model more robust, more explicit, and hopefully that will enable, again, more efficient applications going forward. In particular, something on weakening release sequences, so that if you're using you've got a release sequence in your chain of reasoning on your atomic operations. No, I'm not going to get there. I'm going to say all sorts of erosion and mislead. Go look up the paperwork on this if this is an area that matters to you. Coroutines I have in yellow because that's one of my 7 pillars, but it's another big deal for concurrency. We're upgrading standard atomic. So we'll also have support for atomic floating point types in C++20. We will have support for atomic shared pointer and atomic weak pointer. But the thing to understand about atomic shared pointer is you can't dereference it. It's not a shared pointer, it's an atomic handle to a shared pointer. And what you can do, without having to worry about mutexes and synchronization, because the whole point of atomic objects is you use them without synchronization, you can load that shared pointer state into a non-atomic shared pointer, and then you can manipulate that quite safely, because you've now got that non-atomically in your thread, but don't hit that object from multiple threads. And that means, all the various atomic operations to load, store. So that's what atomic shared pointer is, and that's why we're deprecating the old API, where shared pointers were under the restriction they had to be treated as if they only ever used the atomics API. You could not dereference them, whatever. You had to load them into another shared pointer to use them. But that was not at all catchable without just simple code auditing. It was a very unclear API, and yeah, we're very happy to deprecate that and replace it with something that's actually in the type system. We're also going to require, not landed yet in the pipeline for Cologne, that on any hosted implementation, there will be at least one lock-free atomic integral type. You can at least have a guarantee that your architecture will support at least one lock-free atomic type, which is really kind of useful. That requirement is still going to be optional for freestanding implementations. But for the vast majority of us, we can now assume that there will be lock-free atomics, and there'll be some type defs to the most performant ones that, whichever integral type size they map to, we will get, I know this one's lock-free, this is your default lock-free one to use. And we're adding a notify API that says when atomics do certain things, I can notify people. I haven't really got my head around this. This is again something that's landing at the next meeting. Hopefully I'll have more to say about that when I understand it more. Atomic ref is almost like a primitive building block to build standard atomic out of. This is putting an atomic wrapper around a non-atomic type. But hopefully more efficient than just straight using a mutex. I don't understand the magic behind all this, I just help them write the words and hope the folks doing this know what they're doing. Turns out when we standardize the parallel algorithms for C++17, we omitted an important use case, which is vectorization, but not across multiple threads. Vectorization is just within this thread. So by adding that missing policy, it doesn't do a whole lot of good for all the algorithms, but there are certainly a few where it can make a big deal. So to really support those, we're just adding the new policy. Synchronized O-stream buffer, because when you've got multi-threaded code, the last thing you want is interleaved writes, because different threads were writing to see out at different times. But having a special type just to guarantee that we get control over the synchronization so that different whole buffers land appropriately. Latches and barriers are currently under review. They should land at the next meeting. And JThread, where J is for joining thread. And the big deal here is it's trying to be a second catch at some of the sharp edges in standard thread. And in particular, it supports cooperative cancellation, which has been a long requested feature. Moving on. Concepts. This is another show of hands. I'm at C++ now. I have expectations of my audience, but you are allowed to disappoint me. Who has a reasonable idea of what they expect from concepts? Who doesn't know what I'm talking about at all? Okay. Just putting a few hands holding themselves down, but mostly we're on board here. Concepts that we're landing is based upon the C++ 14 concept TS. We didn't update it for C++ 17, and when we looked at updating it, we said, no, it's ready. We've got a good idea of what this feature should look like now, and we do not want to miss C++ 20. So it was one of the very first features we landed in C++ 20, which has given us time to refine and poke at it and clean it up a little bit. In particular, we addressed some design concerns around what was deemed to be the terse syntax, which is templates that don't have a template head that like, make it clear you're dealing with a template. And general notion of concepts, it's a way of describing constraints on generic code that you use to guide template instantiation. So where you might use enable if or this finite tricks today, this is putting that kind of information directly into the compiler. A type system for the type system is the way I want to describe it. That's not quite what it turns out to be, but it's like a type system for runtime programs is what you're trying to put into the way you control parameters in your generic programs. So, the main features. We get requires clauses, which are simple predicates that we use to constrain code to say, if I satisfy the requires clause, I can instantiate. If I don't satisfy the requires clause, keep looking, I don't exist. Concepts are essentially named collections of a group of constraints, a group of requires. And that says, this common set of things that all work together, I can give that a name, which gives me a higher level abstraction that I can now write code that's much cleaner, easier to read, and we know what we're dealing with. Constrained auto is our answer for the terse template syntax we had before, where I have auto and then put a concept name after that. That now constrains deduction on that auto. So in the way you used to have auto in polymorphic lambdas, we're now promoting that into regular functions. You can have auto concept. It's effectively a hidden template, but you know at least where the template parameters are coming in. If you did use the concept TS previously, this is largely the same feature without the keyword auto there. That was our answer for disambiguating for people who are uncomfortable with, I see an identifier in code and I don't know whether it's a type, a concept. If I've mistyped it, I don't know which way it was supposed to go to fix it, which makes it really hard for compile diagnostics. And the final part of the whole bundle of concepts is what we call subsumption. And this is how you get to guide overload resolution when I have multiple templates that actually now do have the same argument list, because I've overloaded on requires clauses and concepts rather than multiple arguments or different types. And that says when I go through my deduction rules, whichever is the most constrained of the concepts or set of concepts that I satisfy is the one that is the best match. So just a couple of quick examples. I don't really have time for examples in this talk because I've got so much to cover. But yeah, I'm having a hard time between the screen's relatively flat to me when I can poke here and you can't see. So a simple idea of defining a concept. Concept assignable equals. So it's not your embedding code or anything, it's concept name equals. if you went back to the concept TS, it would be a concept bool assignable equals. But all the concepts had to be bool. There was never intent to be anything else. So we finally managed to remove the redundant keyword. So it's now just bool concept equals. And here's a predicate. We can see I'm using some type traits here. It can be defined in terms of any compile time constant expression. I'm also using some concept here. Common reference is a standard concept in the standard library of C++20. Doing some clever tricks here just to say, okay, I need to have on the left-hand side of my assignment, I'm going to have an L value. I know this because I have the requirement that is L value reference LHS says LHS is an L value, therefore I can hopefully assign to it. I'm going to remove const just to make sure I've got a non-const thing to, when I'm doing my evaluation, to understand what I'm talking about. And then we come down to the requires with this syntax says, inside the curly brackets, I'm going to have a sequence of expressions. And those expressions all have to be valid code. If I can find everything I need to instantiate that, then that satisfies the requires clause. So this hopefully makes it much easier to describe and guide the kind of things we're trying to talk about. In general, it goes a bit more complicated. And my second example is a very quick example of the constrained auto syntax. So auto sum, auto stud integral x has to be integral type, but I don't know which integral type. Auto integral y is another integral type, maybe the same, maybe different, I believe. And then I can just return x plus y, which I know is going to work because they're all integral types.
Can the return type be a constrained auto as well?
Can the return type be a constrained auto as well? I don't believe so, because the return type is a type, whereas a constrained also is saying, but whether it could be a constrained decal type auto, I don't think so. I'm sure we're going to get all sorts of interesting questions as people get more experience with this and maybe in C++23. And that's about all I'm going to say on concepts. As I say, all of these things you'll find much bigger talks that will go on the whole 90 minutes beyond on most of these topics. Contracts is one of the fields I've actually been working on myself, so I know a little bit more about this area. And it was recently described back to me by a colleague at my office that what we're doing with the whole contracts facility is it's a way we can integrate through the toolchain essential truths about the underlying code. And with that, there's two obvious applications that people who have been working on this feature are trying to make that address. One is you want to verify that truth and say, you know, I've told you this thing's true. If you find it's not, tell me about it. I have an error. It's very much a software quality improvement, trying to bring into the software development process some of the tools we need to help produce robust software easily and efficiently. There's a second strand of folks who want to come at this and say, once I know about those truths and the compiler knows about those truths, I can generate more efficient code. And that's also, second application, the same kind of space, so they're falling under the same kind of design. There's a bit of tension there. So the basic syntax. It's using the attribute syntax. We have called the first token assert, which is essentially either assert, familiar from existing uses today, pre and post for this is a precondition or this is a postcondition. And the intent here is that pre and post go on your function declarations on the signature. And the preconditions are evaluated before entry into your function. And on any successful return, the postconditions will also be evaluated. Depending on when I get to the start talking about level. Asserts, on the other hand, go inside the function definition. And therefore they go immediately before or after the particular piece of code that you're concerned about creating those affirmations on. In conjunction with where the assert's going and decorating the code, we have the notion of a checking level. And this is just to denote to your runtime system how expensive I think it might be to evaluate that check. I don't want to pay for super expensive evaluations in my production systems, but maybe I can afford the regular cheap ones. In particular, if I have a constraint that checking that predicate, such as on is sorted, or opposed to checking the predicate might be more expensive than the actual cost of the operation. Classic example is the post condition on sort. Yes, my rate output sequence is sorted. That's relatively cheap. That's linear compared to n log n for evaluating sort. That's a reasonable thing to have as a default check. But the predicate people often forget about is it's also a permutation of the original sequence. That's not something I can validate in the same compile time as the actual sort function itself. So I do not want to be evaluating that check all the time. But if I'm in a really hard debugging scenario, and I've got the ability to inform the compiler these, if I can turn the switch and say, okay, I'll pay the expense, run those extra crazy checks, because I'm still trying to dial down on why my program is behaving strangely, they would then be available. And the final check that we have here is something we're calling Axiom. And the name is getting more and more controversial as time goes by. And guess what? I've sorted it to the expensive end of checks. This is a check that's so expensive, it never ever runs. Other folks describe this to me as, this is a check that's so obvious that we never need to check it and it never runs. And therefore it's nothing but a compiler hint to the optimizer, which is, we're into a bit of tension and we'll be having an interesting time at Cologne narrowing down the final details here. But the notion of Axiom as why would I have checks I never run? Well, if I have a function, I can give it a semantic and well document and describe it, such as is a valid pointer or is a valid range. So I know that I've got two input iterations, but they do form a valid range. I can't actually perform and execute that function, but I can describe it. It's never going to be of any use to the compiler to generate and try and run that code because it can't do it. But static analysis tools can be aware of the larger vocabulary of some of these functions that might be used axiomatically to say, this is a property I want you to be aware of, and that you can apply to your own internal chains of reasoning and help find flaws in my logic. So it's a useful way to inject additional information to the program that you might not be able to execute at runtime. So regardless of your reason for putting axioms in code, the one guarantee is there will be no compiler switch that turns them on, because that would defeat the purpose of having these things that don't actually have definitions. Actually, before I go on, the one thing I've not talked about there is in the syntax, after level, if you've got a post condition and you want a post condition on the return value, you can put a little identifier there to name what the return value is in the context of that predicate. So that's how you actually do post conditions on what did the function return to me. The other part of contracts, we say when we're using for error detection, is if at runtime I detect the contract is violated because I'm in a mode that's doing that check, we're going to invoke what we call the violation handler. We're going to pass it some information about the source file, the function, the line that was executing, and the predicate, mostly as string literals. And by default, it's just going to call terminate. Not terminate, sorry, that's failing of the exceptions handling system. I rag on everybody else who uses that term here, and here I am doing it. It will call abort. There will be an option that you can instill your own custom violation handler. But the only way to do this will be on the command line of the compiler itself. There will be no source code way to interact with the violation handler. And this was a big concern from folks involved in the security community. Anytime you put in a global callback that can be accessed from anywhere in the system, it's a big hole for security exploits, especially the nature of these things can be getting called out of kernel code in all sorts of places if you want to use the facility well. So in order to constrain our exposure to a bunch of security issues, the rule is you do not have the ability to set or inspect the violation handler at runtime. If you desperately need this ability, you can install a violation handler that delegates to some symbol you do know the name of, and that you do have the ability to, but you're effectively injecting that feature yourself. You are writing your own security exploit if you want to do that. But we're not going out of our way to make it easy for you. As for what the violation handler is going to return or contain in terms of the source code place that failed, the easy thing is I'll just give you everything from where the source line that had the assert. What you really want, and we're encouraging a quality of implementation, but we can't guarantee, is that you want the person who actually made the call, their information, because they're the one who violated your contract. If I'm calling you and violating the preconditions, the bug's not in the code that's checking you violated the precondition. The bug is in the code that made the call. So ideally, we'll get the call site information of, or the violation handler will have the call site information of where the call was made. Early days, we're still to get through, see how these features shape. We think that's possible. On the other hand, if I'm really concerned about overhead, is just adding too much overhead to my system, I could just go with empty strings and zero line counts, just so I've got the feature it's going to detect and abort, but I've minimized all the static storage space of all those different strings from throughout my system for a really tight release package, perhaps in embedded systems and so forth.
So, like you say, like the handler is going to be specified on the compiler command line. Is that like the main symbol they do for like operator new, or like for instance, if it's on the compiler command line, do I have to recompile my libraries to use my handler as well, or is it just like a linker magic to?
So the question is, how do we actually specify this on the command line? And I'm afraid with all these things, it's implementation defined. I'm going to have a function that I want to call, presumably defined in one of my source files, and ideally I will specify that on the main application, because that's the thing that, and everything else is going to delegate to whatever the active violation handler is. But early days of getting our experience with the tool systems.
Is the contract error detection only at runtime, or is there also some compile time?
Question is the contract error detection only at runtime, or is it also at compile time? Yes. We're giving some, in most cases where it's not an axiom, code that can be checked. If a compile time can reason about that code, maybe it's all const expert, great. Then we're certainly enabled to do that evaluation at compile time. If it happens during a const expert evaluation, which is always possible, I'm allowed to put contracts on my const expert functions, I'm using it in a const expert context, it's being evaluated at compile time, and I violated the contract. Well, that's now a hard error because I've gone beyond the amount of what that function is permitted. It's the same as having undefined behavior in a function that's got to be detected. If I've got a contract violation in evaluating a const expert, then that is also now a hard compile time error, and I will hopefully get a much nicer diagnostic about that because I've got the expression I was asserting on. Sorry?
Are contracts also checked in release builds or only debug builds?
So the question is, are contracts checked only in debug builds? Are they also checked in release builds? As I said, we saw there were three separate build flags there. We've got the default, the audit, and the axiom. The intent is that by default, if you don't specify any other command line flags, the default checks will run, the audit will not, and you cannot enable the axioms. You can certainly disable the audit, the default ones as well for your release builds if that's what you intend to do. The standard is not going to mandate what your command line does or even how it says this. It's simply saying you have the options to do this, and the assumption is by default you're running with them on, but you have a switch to turn them off.
Is there a way to turn them off per module or per
So the question is there a way to turn them off selectively per module, or at a header granularity, or is it basically just global to the whole system? Time will tell is my answer here. The intent is we would like to be able to do this very fine-grained. But then you get the question with inline code and templates as to which instance do I violate the ODR if they end up meaning different things. And by the letter of the law, no, they don't. Because the ODR is, are these things token for token the same? And yes, they are. But some people are very uncomfortable that they could still behave very differently. So this is in one of those grey areas that people are still trying to tamp down for Cologne.
Well, what is this problem exists today with like regular asserts, right? Because if you have one library built with like assert enabled, and then you build your code with asserts disabled, but you link against the library that has the asserts enabled, then you don't know which template dispensation you're going to get.
So the comment is we already have this problem with the CSUT facility today, and it's subtly different because there you are violating the ODR because the macros expand differently and you get different token streams in the actual defined function. Whereas we're doing an end run around that by putting it into the language. So technically we satisfy the ODR, but in practice some people are very uncomfortable about that. So it's to some extent an ongoing debate, but it's not top of our list at the moment. We're still trying to balance optimization versus integrity of checking and making sure that enabling undefined behavior here doesn't suddenly mean lots of time traveling code behaving differently, especially omitting checks I was asking for. So again, that's coming down to the while we're going to be settling a bunch of those corner case issues in Cologne.
I just wanted to mention that because side effects are extremely strongly discouraged in contract predicates, whether a contract check occurs or not in a correct program doesn't matter. So whether it happens, in other words, it is mix and matchable for a correct program. For an incorrect program, you might get a check, you might not, but it's better than nothing.
So the statement there is, for a correct program, it should make no difference because if you never violate a contract, you're just going to get good behavior all the way through. I'll leave it at that. Coroutines. This is the one I'm dreading because I really haven't got my head around coroutines yet, but it's one of the big things people need me to talk about. So I'm going to make my best effort. If anybody here understands coroutines, please correct me because I'm sure I'm saying some things wrong here. I'm still not quite, I'm giving it a shape of the feature, but anything I say about how it actually works is almost guaranteed to be a bit wishy-washy and on the edge, but possibly wrong. One side too many. Wrong way. Okay, don't let your hand slip onto your notebook while you're presenting. Bad things happen. But yeah, the basic idea of a coroutine is it's a resumable function. It will leave its execution back to where it was being called from, and then be able to return into its current execution at the point it left off with all its local variables in the same state. And there's certain programming models really benefit from this. In particular, asynchronous coroutines will be able to resume on different threads. And when you combine that with thread pools, this turns out to be an awesomely powerful technique for chaining logic for asynchronous large-scale systems. And that's the big motivation behind trying to get it into the language as part of the concurrency and parallelism work. But it's also a really useful feature in different ways, just in regular synchronous code. So when it comes to implementing a coroutine, relatively simple. You return a type that satisfies some constraints described in the library that says, yeah, I'm the kind of thing a coroutine can return. I have the special information that a coroutine knows about for storing away the information. Just let me go back and resume. The actual coroutine body itself will use either the words co-return or co-yield to indicate co-yield, go back and be in a state to resume, and co-return, go back and I'm done.
And I can't use the normal return keyword?
And the question is, can I use the normal return keyword? No, because normal return keyword is going to try and return, well, I don't know how to construct all that external state that the coroutine facility is modifying for me. The original proposal did use the return keyword, so the generic code, they would be fairly interoperable with functions, but they behaved differently enough that there was an impetus to say, it's really subtle for me to understand when I'm looking at a function or a coroutine if they use the identical syntax. So we go with this co_return in order to make sure that the return from a coroutine is distinct, and I can now know on site I'm looking at a coroutine. Likewise, the keywords await and yield, They're new. They didn't have this problem that they needed the colon to score disambiguator. But for consistency, it was deemed to be nicer to do this, or uglier to do this. But yield was a really awkward word to try and turn into a keyword, so it did solve one of our headaches we were having. So once we brought co-yield, co-awake came along for the ride. And co-awake is part, how you invoke another asynchronously into a coroutine, I believe. Go see anybody else talking about this. It's a really important useful facility of C++20. Gornishinov has some great tutorials about this online, and will express this far better and far more correctly than anything I'm going to do here. But do look into this. This is going to be a big deal for C++20. And final note, the feature itself is fairly customizable. There's this machinery behind the scenes that's going to be managing the external state of what's in your coroutine, how I can get access to that in order to go back when everything resumes. You actually have the ability to customize and manage that if you know specific things that can optimize that scenario in your code. So, experts level feature only, but we have plumbed all the way in that you can eliminate all the fat that might be expected from a facility like this. Comparison operator. In a nutshell, we have a whole new operator coming into the language, the spaceship. It supports three-way comparisons, so is something less than, greater than, or equal equivalent to something else. All in one operator. And unfortunately, different types have different kinds of capabilities here. So some things have a nice strong equality, A equals B. I know what that means. Some have a fuzzier equality, a weak equality. So things they might be distinct, but they might compare equally. Things like a case-insensitive string comparison. So multiple values might interoperate and compare as equal, so it's not a one-to-one mapping on your value space. And you would have this as the return type for types that don't actually have a relative ordering. But as soon as I can order types, I have the same question. Is it a case-insensitive string comparison type thing? If A is less than B, does that guarantee, and B is less than C, does that guarantee A is less than C? So we've got a scale, again, a spectrum of different qualities of how strong an ordering my type actually induces. And in all cases, the weak equality and strong equality will implicitly convert to bool. So I can use them in a regular equals context, like I would in a regular equals context. And likewise, the different orderings convert to essentially an integer that will be negative, 0, or positive. And that gives me the more traditional handling of the three-way comparison.
Just a question, did during the standardization anyone wrote up that there are actually cases in real-life programs where you have a type which has both weak and strong equality?
And the question is, did we discuss in standard that there are types that do indeed end up having both strong and weak guarantees here? We discussed so much in this space, I believe it had to have been covered at some point. Trying to get this right, we landed it early, so we had time to iterate and clean up and fix parts of the design related to how this might impact us. For types that are really that awkward, maybe you just don't define the spaceship. If you can't give it the semantic that you want it to have, if you want it to be ambiguous, then it probably isn't the right operator for you. Because your type is already that awkward that trying to use this kind of value semantic is probably the wrong interface. So, comparison in a nutshell. Yes, it's a new operator. You generally define it as a friend operator in your class. So it's a free function, but it's only found via ADL and not by ordinary name lookup. And this is a new library idiom that people are getting behind in a big way in C++20 because it simply reduces overload sets from what ordinary name lookup finds. And that is going to ease compile time because when name lookup says, I found 392 different equality comparison operators. Which one did you want? Now I've got to run all my different algorithms and these aren't always linear. So having large overload sets or sets to pare down in overload resolution, the more we can contain those for common names like operators, the better. We've yet to land a facility that lets us properly equals default them, but that is coming in Cologne. And that will simply do, essentially a member-wise structural comparison at the same granularity of return type, the most restrictive of the types in your type. And we can similarly now equals default just operator equal equals as of landing in Cologne as part of the same piece of work. And finally, we're adding two new algorithms to the standard library. Compare three-way to compare two values, and lexicographical compare three-way to effectively compare three-way to each element of two sequences to determine which of the sequences it gets the three-way comparison. That's comparison in a nutshell. Compile time programming. Yay, concepts we've already been through fairly quickly. Templates and context are the two main techniques people are using in compile time programming these days. And there's always the preprocessor as well, just for a little cleanup at the end there. So, what do we get from templates? One of the big deals people have been asking for a long time is, can I have non-type template parameters like int on my own class types? So I've got a string type. It's a literal type. One maps a string literal or something. Can I use my string type as a non-type template parameter? As of C++20, the answer will be yes, if you obey all the rules. In order to be usable as a non-type template parameter, you have to be a literal type, so you actually create compile time literal values of your type. And the compiler needs to know, I'm doing deduction, are these things the same? And it does that by relying on the type that you use has a defaulted spaceship operator. And the default spaceship operator is defined to do nothing but structural comparison of all of its members and bases, and recursively that rule applies to all its own bases and members. So as long as you can just default the spaceship operator and context for all your constructors, so your type is now a literal type, then you can have we'll able to use that type as a non-type template parameter. I suspect Hannah was talking about this in a keynote earlier in the week. Lambda templates are my term I've quickly come up with where you have generic lambdas, polymorphic lambdas today. Rather than using the auto keyword to create that, we can also now introduce a template head to say, okay, here's some template parameters, and now use those like I would, as if it were just declared with a template keyword on the function call operator of the lambda. I have a quick example of that coming shortly. Expansion statements for ... Unfortunately, I missed David van der Voorde's keynote. I don't know if it's something he was talking about or not. I know he's the author behind this. I'll defer discussion of that to a slide I've got coming. But again, that's something landing in Cologne. What we do have that's quite neat is we're reducing the requirements to redundantly specify, I say redundantly, type name and .template. If you go back to the good old days of C++03, the rules were, if you had a dependent name, you had to use type name or .template. In order to disintegrate to the compiler, I intended this to be interpreted as a type and expression, not as the other thing you might have interpreted it to by our default rules, trying to keep the parsing as close to C as possible. Those rules were really hard because if the type name was not dependent, you were not allowed to use the keyword. So for C++11, we relaxed the rules against redundant use of type name and .template. So people didn't have to think as intuitively as a compiler anymore. They could just, I'm unsure, I can scatter it in, and template code just works. Maybe we'll be putting in a bit more in than we need to, but do I want to be a superstar showing off that I know when and where I can precisely use it? I like to, because I like to understand what my code's doing. It's a real hint to me. But it made templates much more approachable for many folks. But we're getting the issue that every time we get an issue where I was supposed to use type name or .template, and it fails to compile. The compiler knows a reason. It's there in the fix-it hint. It's telling me what I was supposed to do. So why don't we just let it do that now? So that's finally going to not completely eliminate these rules. There's a few corner cases that we really do need to disambiguate, but it will be a lot simpler at many more places. Now that Microsoft have finally got their compiler to do the right thing, we're telling them, yeah, that's okay, thanks, but we can now go back and start omitting them all again. But we do still expect the correct two-phase name lookup rules. So that was still good. Another interesting corner case is we're going to have ADL when ordinary name lookup fails. I don't know how many people were ever bitten by this issue. I was bitten by it all the time, every time I sat down to write my fabled, I'm going to implement tuple again. I have a really nice clean implementation, and my functions were therefore called get angle I angle of something. And, well, I hadn't included something that made get available yet. I'm expecting to get it via argument-dependent lookup. So ordinary name lookup fails. It doesn't find a get function. I've not included something that actually declared a get because I don't know what I'm going to be going get on yet. And at that point, I get a hard time with it. It doesn't go, oh, you failed to find this, but I might find something in argument-dependent lookup. So the rules are now if it sees an angle bracket and it gets a hard error in name lookup, it says, you know, that looks like it might be a template. And I'm passing in a template, so I will defer the error now until phase 2 and try again with the argument-dependent lookup in phase 2. So a lot of places where the intent was to get an ADL customization point or some kind of ADL lookup to get my user, you know, probably a .template get or something, it's now just going to work. And accessing rules for access checking rules for specialization. This was an awkward corner of the standard that says if I've got a private class or structure type within my class, and I now want to specialize another template for my private type, well, that specialization goes outside my class. And my type's private, so the compiler can't see it to specialize it. I don't have access to do that. And some compilers allowed this as an extension, and some didn't. And now we're just saying, yeah, the intent is that you should be able to actually specialize your templates even on types that, oh, you still got to have access to that type in order to use it, but it doesn't rule out the actual specialization. So a couple of quick simple code examples. This is my use of the Lambda template. So I'm implementing swap for tuples. I'm going to go through and call get on each element, call standard swap. I need to be using it because otherwise the name gets hidden as it's a member function. So I do my swaps and then do a fold expression over the comma operator in C++11. This all just works quite nicely. What I needed was a parameter pack of size I, so I could iterate through and I had to do the expansion. And that's what the index sequence library type gives us. It gives us a type that's parameterized on different set of those. So I get my deduction size here. This just works, and I no longer have to write some crazy implementation detail function outside of my implementation itself here. So I can now make things much more local. That's quite nice. But we can go on better. This is the expansion statement I was talking about and said nothing about earlier. The idea here is for ... is our new syntax. And it looks like a range for loop. We have an index, in this case size pi, and the thing on the right hand side, it can just be a parameter pack, and then just matches in each iteration gets to the next thing through the pack, or something that satisfies a scripted binding API. And unfortunately, I put it in pink because at the moment, index sequence does not satisfy the scripted binding API. So this would not actually strictly work. I'd have to write my own thing that did the right customization. But I'm going to try and write a paper in time for Call to see if we can get that added. If not, it's easy enough to write. And that then just gives me this nice simple for loop, which actually expands into, it does each iteration as a separate scope block. It's as if I just repeated that code with the appropriate instantiation each time. But if I want to apply the same pattern over some parameter pack, this is going to be a much easier way to write that, as opposed to you sort of having my strange cast of void, so that user-defined operator overloads of comma didn't interfere with my fold expression. And yeah, I don't even have the funny lambda inside here anymore now, so that's quite neat. The other thing we have with compile time expressions is context bar. So again, David Van Voorde was talking about it. It's quite a bit in one of the open keynotes, so I don't want to label this too much. But one of the big deals to me is constantly evaluated. We'll add dispatch on the evaluation of a context bar function to say which algorithm do I want to use, the one that might be less efficient but guaranteed to work within context bar compile time, or my more optimized runtime evaluation. We're relaxing constraints on lots of things that previously you were not allowed to do within context bar functions. Virtual calls being a big deal. Dynamic cast polymorphic type ID kind of falls out of virtual calls. Try catch was, it's almost a why not. You are not allowed to catch exception to context bar functions. We do not enable that control flow. But as long as your evaluation of that function at compile time never throws, we shouldn't reject the syntax that says I might invoke it with different values at runtime that do throw. So we don't support catching exceptions in context bar, but we're no longer going to reject functions just because they use that syntax. Changing the active member of a union was a peculiar thing that you couldn't do in context bar functions. And all of this is going to make it much easier to implement standard variants in various ways now, because that's got some fairly strong context bar requirements. And the last part coming at Cologne is default initialization of trivial types. Yeah, to speak myself up, my base is not quite what I thought it was. Immediate functions are functions that execute only at compile time, and therefore never need to have even the function body emitted into the runtime at any point. So it's a way to, again, optimize some parts of your infrastructure when you're doing compile time programming. Const init is going to be a way to force constant evaluation or constant initialization in program startup of things that are not necessarily context bar themselves. To say, I want this initialization to be completed at compile time, but the thing I'm initializing is a variable for use throughout the rest of the program. It's not going to be constrained by being constant, just the initialization one. And the big deal coming, context bar containers, string and vector being the main two examples, but in order to get here, we've got to solve the problem of dynamic allocation at compile time. And we're at 89% of the way there. We've got a good model that's extensible and usable by you as well as just by the standard implementing vector and string. What we can't do is multiple layers of dynamic allocation. So a vector of int is fine, a string is fine, but a vector of string goes beyond what we can see with compiler technology today, how we can solve that problem. So within that constraint, only one level of dynamic allocation, we're going to have at least some big progress there. That's going to unlock an awful lot of useful features for reflection type APIs. Now the preprocessor end, we get VA opt, which is a way of optionally putting things into your macros. Mostly this is to handle commas around double underscore VA args double underscore. If you've got an empty VA args preceded by a comma, the comma's got to have something following it. But if you don't have the comma, you can't have the VA args, so it makes it really awkward to have variadic macros being called with zero arguments. And this is the minimal preprocessor hack to let you write macros that can work within that constraint. And finally, the feature macros that have been semi-standard, being maintained in documents outside the standard, that just give us a portable way to try to detect, as experimental compilers implement these features, we have a way to detect consistently across all compilers, do you think you support this feature yet? And that's going to be preprocessor macros coming out of the compiler, and in the library, there'll be in-library headers as well. And there's more, but I've only got 5 minutes left. So, yeah, it's supposed to be here about 20 minutes ago, unfortunately. Lambdas. We've already talked about the the template form. We're going to allow pack expansions in the capture list now. We can then re-expand within your lambda body if you're using one. Stateless lambdas will be default constructible and assignable, just like they were an aggregate that had that as their body. We'll now be able to use lambdas in an evaluated context, so deckel type and so forth. So query, what's the result of computing this lambda if I were to try? We are now like this in the capture list and saying that's how you should do this rather than relying on the implicit capture, as I mentioned earlier. And we've simplified some of the rules of the grammar around implicit capture. You can capture a few more things now. Don't have the details to hand. Aggregates change in every standard. Aggregates are basically arrays or classes that follow certain rules. In particular, they're not allowed to provide have user-provided constructors or destructors. Didn't say what's the other term? User-provided means you've actually provided a definition. User-declared. You can still have user-declared ones that equals defaulted or equals deleted. And for C++ 20, we're saying deleting them leads to things that, as I said, they can be constructed through the aggregate initialization syntax, even though it looks like we're trying to go through a deleted constructor, so why is that working? So we're going to say those things are no longer aggregates, and therefore the deleted constructor will kick in, and those you might have existing code that tells to compile. But it gives us a cleaner model as we're trying to just describe and manage these things. Next thing is aggregates can only be initialized with curly brackets, which means you have to use the curly bracket initialization form, which unfortunately has certain constraints that it will always reject narrowing conversions. You can't use it in a standard library where you go through allocated because the algorithm there is specified, or with new, is specified using parenthetical initializers. So a few places in the grammar and the library, we have things that actually require things to be initialized with parentheses. And if I had empty parentheses, I could value initialize an aggregate, but I couldn't do anything else with it. So we're now going to allow parentheses here, which will open up additional places where aggregates would suddenly break your generic code, which is really unfortunate. And we're also allowing the C-like designated initializer syntax for brace initializing aggregates. A couple of new attributes. We have no unique address, which is a much nicer way of doing the empty base optimization. Just say this thing, apply it as if it was being used by the empty base. Likely and unlikely to be branch hidden predictors on your conditional code. Standard and reason why, even though it's not an attribute, it's coming with the same notion of being this, and like in the source, I'm telling the compiler, you shouldn't be able to reach the code here. It's my way of saying you shouldn't be here. If I've got here, there's an error. Let me know about it. And the idea also for no discard is an existing attribute, but be able to apply a text string to say why you intended to, what you were trying to say by putting no discard there. I have 90 seconds. Unicode. We're updating the way this Unicode standard. We're introducing char8t as a type that represents Unicode, encoded as UTF-8, and requiring that UTF-16 and char16t and char32t string and character literals are encoded as UTF-16 and UTF-32. There's one case we're dealing with in Cologne about what happens if I try to output a Unicode string that says, well, I don't have a stream is ready for the new type, therefore do I write out the pointer value? Sorry, I don't have time for questions, I really have to move. Structured bindings, we've cleaned up a few corner cases there. I'll not walk through them, but a few places where they would catch you out by surprise, that why did the compiler not allow this, we found them and we fixed them. Explicit bool, just to say, here's a Boolean expression that says conditionally whether or not this constructor should be explicit or not. This is defined namespaces. We're now opening up a namespace. We can do, since C++ 14, I think we can do namespace A, B, C. But if one of those was an inline namespace, we couldn't do A, inline B, C. We can do that now. Default member initializers for bit fields. Hopefully the name says it all. Default initializers being when you put them in a class definition. Efficient size, the delete for variable size classes is trying to do the C-style thing of adding extra padding off the end of your classes at runtime. array size reduction in new expressions. And this is big. If you default your copy constructor and one of your data members is something like auto pointer that has a really funny copy constructor, that would be an error today. Whereas we're going to say, well, we know that what we're supposed to synthesize from the member. So even though you wrote me const x, const tref, because I'm in generic code, I don't know how to spell the copy constructor for t, I will now give you the right signature. Something to do with pointed to members, and when you've got a const ref can be treated like a null value. And you've got reference qualifiers on your member functions. There was a slight mismatch there, so that's been fixed to play smoothly. I mentioned checking for abstract class type. Range for statements, we can now have an initializer like you can on if statements, so that can again scope the thing that you're trying to perhaps iterate over. And turns out there's an open corner case in for loop customization points that if the thing you're trying to iterate over has just one to begin and end as a member function, and end was not unusual, it said, okay, I don't find them both, that's not a range. Whereas when I say, okay, if I find just the one, I will continue with the next step of the rules and see, well, can I find them as a proper range as free function ADL customization points. And a bunch more stuff that I don't have time to get into that will be landing in Cologne. But it's on the screen so you can read it. On the final slide. Library highlights, stuff. I have to have a slide on allocation before I'm done. And already experimental compilers shipping. You can track some of the experimental features that become available through this website here, which is easily found on the front page, as a link on the front page of the isocpp.org website. And with that,
all right.